Newton's method is used to calculate the approximate values of roots of a function where it is not known how to get the zeros of that function, or it is very difficult and time-consuming to do so. So Newton's method uses a series of guesses in order to get the approximate value of a zero. And in order to explain this, it's best just to show how Newton came up with this idea, because it's very insightful. Normally I just show how to use it, but it's kind of weird just to see how it's used without understanding where it comes from. So I'm just going to show where it comes from, as opposed to showing how to use it, because how to use it is very easy. So first of all, if I have a function where it's very difficult to calculate the zeros, or it's just not known, something maybe just like 48x squared plus 3 to the 90th minus 47x plus 3 to the 45th. It's not going to be possible for me to use something like quadratic formula. There's even a cubic, and I think even for a fourth root, but anything above that, there is no formula for the roots of the zero. It might be possible if you really wanted to use like the rational zeros theorem and try to use that, but I mean, that'd be pretty crazy to try to do something for this high. So what Newton did was he used this idea of the tangent lines. Well, first off, let me just explain this first. He used the idea of the tangent lines. Actually, let me just show exactly how it's done, and then it will be obvious what he did. So first off, what he did was just picked a random point that was near the root. Often what he would do was graph these functions, come up with an approximate graph. Now the graph wouldn't really be able to tell you exactly where that zero was, but you can kind of get an idea of like where it might lie. So what he did was picked a point near where the zero was. Didn't know where the zero was, but just had a random guess. And one thing he noticed, this is going to be hard to draw. Was that the tangent line intersects with the x-axis. No matter how this curve is going to be shaped, if it's shaped up, it eventually will make contact with the x-axis. So what his idea was to do was to make a guess, have this point intersect with the x-axis, like so. So this I will call, so this is x1, I'll call this one x2. And then to put this point, x2, f of x2, in. So now he found this point, and then he's going to take the tangent line of this again, and he gets another point, x3. That's going to be about here, and this is x3, f of x3, and do it again. So this will intersect here at x4. This point is x4, f of x4, and then again, I mean, you should be able to see the picture here by now. Oh, I didn't mean to do that. So here, now I'm at x5. So these tangent line intercepts are going to get closer and closer to r until it's infinitesimally close. These intercepts will never actually equal r because I'm going to continue to be taking the slope of something that's just in front of r. So this will get infinitesimally close eventually here, and then the tangent line will be like right here, and then x6 will be somewhere here, and x7 will be somewhere just in front of it. So what he's doing is these approximations are getting closer and closer. So what he's done is taken a guess. So here, let me change the color. So here, he's made use of the fact that while this 0 might be difficult to calculate, it's easy for me to calculate the intercept or the 0 of a line. That's really easy to do. So here's the equation of a line. And when I make the guess, I'm already knowing what the x is. I'm just picking a random x. And then the slope is easy for me to calculate. I just take the derivative of this. Now, while this is like large and clumsy looking, it's not really difficult to take the derivative. Derivative's easy to find. And also, finding a guess is easy. All I have to do is just put in x, whatever x I want to do. If it was 1, then this would be really easy to solve. If it was 2, it would be easy to solve. No matter what number it is, solving for y of this equation is not hard. So finding the derivative is not hard either. Solving for the derivative is not hard as well. So using these facts, we're able to come up with a way of finding an approximate for this 0 that would otherwise be very complicated. So he uses the fact that these x-intercepts will get closer to the value of this root. And what I'm going to do is find the 0 of these successive tangent lines. So what I'm going to have is y minus, and then the y I've got is whatever f of x is, equals to the slope. The slope is whatever the derivative of the function is, and then times x minus x1, which is whatever the first point is. Now the y, I'm going to know what that is because I'm looking for the point at which it intersects with the x-axis. So y is going to be equal to 0. So 0 minus f of x is equal to f prime. Oh, this is x1, by the way. F prime of x1. So I'm going to rearrange this. I'm going to divide out by f prime. So minus x. And then I'm going to add x to the other side. So this is Newton's formula. And it's normally written like this. X to the n plus 1 is equal to x to the n minus f of x to the n divided by f prime x to the n. So what Newton does is use this formula. He takes a guess at what x is, just somewhere near this 0, puts this x into this formula, into the function. So he finds the function value of the x, and then he takes the derivative of that function, finds the derivative value of that, subtracts it from the original x, and then he gets the second x. And once he gets the second x, he does the exact same thing for the second x. And then once he gets the third x, does the exact same thing. Fourth x, exact same thing. Fifth x, exact same thing. So in order to find a good approximation, what is needed to be done is to do several iterations of this formula. So I start with my first x, I put it into this formula, I get my second x, I put it into this formula again, I get a third x, put it into the formula, get a fourth x, put it into the formula, get a fifth x, and I do it for as many times as necessary. Normally I do it until, it just depends on how much accuracy one needs. If one needs it to be very accurate, they're going to have to do it many times, and a computer can do it many times. This is in fact how computers find solutions to questions like these. It thinks, this is how a computer thinks. It uses its brute force capabilities to calculate to the millionth iteration of this in fractions of a second. But this is the idea behind it. So it'll get closer and closer to whatever the value of r is. And the more iterations I do, the more accurate it will be. The amount of iterations will depend on how far my guess is. Because if my guess is right here, then I don't really need to do as many iterations as if I started from all the way out here. So it depends on a few different factors, but this is the idea. I have a function, I find its derivative, then I make a guess at an x, and then I use this formula, and then I do as many iterations as I believe is necessary in order for me to get an answer with sufficient accuracy.